In this video, we're going to introduce ourselves into the world of quadratic equations. A quadratic relation is a relation that has an equation in the following form. Y equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Whereas you can expect linear graphs to look like these ones right over here, you can expect quadratic relations to look more like a U. One other way to refer to the graph that represents a quadratic relation is a parabola. Now, depending on the exact equation, a parabola can either be pointing up or down and can be either wider or narrower. And of course, it doesn't need to necessarily have to start right at the origin. It can start at anywhere else as well. Alright, first things first. Let's take a look at the standard parabola, where a is equal to 1 and b and c are both equal to 0. What we get is y equals x squared, and the graph would look like this. Why? Well, if you plug in the numbers for x, you would get this particular graph. If you plug in 0 for x, you'd get 0 for y. If you plug in 1, you'd get 1 for y. If you plug in 2, you'd get 4 for y. Awesome. And what about this side then? Well, if you plug in negative 1 for x, since it's going to be squared, what we would get is negative 1 multiplied by negative 1, giving us 1. If you plug in negative 2, it would be negative 2 multiplied by negative 2, giving us positive 4. Notice how we plug in negative numbers and got the same value as plugging in the positive numbers. Great! Now, this point right over here is called the vertex. And like we mentioned before, it does not necessarily have to be on the origin. The vertex can be thought of as the point in the parabola where the curve changes direction. If the parabola is opening up, then the vertex will be the minimum point, or shall I say the lowest point on the graph. If the parabola is opening down, the vertex will be the maximum point, which would be the highest point on the graph. Also, notice how the parabola is symmetrical to itself when it is seen as two halves. This imaginary vertical line that divides the symmetry of this parabola is called the axis of symmetry. Awesome. So before we end this video, I want to compare what we know about linear equations with quadratic relations. A linear equation never has an exponent of 2 in it. Take a look at some of the linear equations on the screen. Notice how we don't have an exponent of 2 anywhere here. Now, let's take a look at some of the examples of quadratic equations. For these, notice how there's an exponent of 2 on the x. This is something you can expect to see from quadratic equations. Well, that's it for this video on quadratic relations and the idea.
What is a quadratic equation?
Here's a quadratic equation. Y equals 3x squared plus 7x minus 5. Hey, here's another quadratic equation. Y equals 7x squared plus 9. What makes a quadratic equation a quadratic equation?
A quadratic equation is an algebraic equation written in the form y equals ax squared plus bx plus c. Check out our quadratic equations here. This is a quadratic equation where a equals 3, b equals 7, and c equals negative 5. This is a quadratic equation where a equals 7, b equals 0, and c equals 9.
Also, a quadratic equation, when graphed, makes a parabola. This is a parabola. So is this, and this. All of these are parabolas. We'll talk more about parabolas in a bit, so hang tight.
Remember, a quadratic equation has a degree of 2, and when graphed makes a parabola.
Hey, by the way, let's remind you of what a linear equation is. Both of these equations are linear equations. A linear equation has a degree of 1. That means that the highest exponent on any variable is 1. Note that all exponents for the variables of these equations are 1. Y to the first equals x to the first plus 7. Y to the first equals 2x to the first. A linear equation, when graphed, makes a straight line. Each of these straight lines is a graph of a linear equation. Okay, that's our refresher for linear equations.
And back to those quadratic equations.
Quadratic equations and their graphs are pretty cool. They help us understand lots of cool stuff. The arc of the high diver, the flight of a golf ball, or of a rocket, the jump of a skier.
Guess what? Each of these motions can be explained mathematically, thanks to quadratic equations. Yeah, let's hear it for quadratic equations, people!
Using math to help us understand these kinds of things is quite beneficial. How about that high diver? How high is that board she's jumping off of? How many twists and flips can she perform before she breaks the surface of the water? How about a model rocket launch at a local park with some friends? Well, if you launch too high, your friends won't be able to see it. Also, you'll want to have an idea of where it will land, hopefully not on someone's roof.
Understanding real movement in the real world does take a lot of complicated numbers and operations. And you'll learn a lot of that cool stuff when you study physics. But hear me when I say this, friends. Quadratic equations are an important building block for understanding this stuff, so learn them well.
A quadratic equation is an equation with a degree of 2. A quadratic equation, when graphed, makes a parabola. Parabola. Blah, 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 blah.
Graphing quadratic equations.
Okay, now let's talk a bit about graphing quadratic functions. We already know that the graphs of quadratic functions make parabolas.
Here's one of the most basic quadratic equations. Y equals x squared. And its graph is one of the most basic parabolas. In fact, let's call y equals x squared the master function.
All right, let's graph this master function, y equals x squared, and see what kind of parabola we get.
One of the simplest ways to graph an equation is to plot points. Plug in an x value, run it through the equation to find the y value. Then take our x and y points and plot them on the graph. If we do that enough times, our parabola will begin to take shape.
Okay, let's give it a shot. Here are some x values we'll use. 0, 1, -1, 2, -2, 3, and -3. That should work. We'll plug each x value into the master function to find the corresponding y value. 0. 0 squared is 0. Our y value is 0. The ordered pair is 0, 0. Let's plot that point here. 1. 1 squared is 1. Our y value is 1. The ordered pair is 1, 1. Plot that point here. -1. -1 squared is 1. Our y value is 1. The ordered pair is -1, 1. Plot that point over here. The next x value is 2. Run that through the master function. Y equals x squared, and 2 squared is 4. That makes our ordered pair 2, 4. Plot that point. -2. -2 squared is 4. Ordered pair -2, 4, plotted here.
This parabola is beginning to take shape. Let's plot a couple more points. 3 and -3. 3 squared is 9. Ordered pair 3, 9 plotted here. -3 squared is 9. Ordered pair is -3, 9 plotted here. And there's the parabola of y equals x squared. So beautiful.
There are a few key features to recognize in parabolas: the vertex, the axis of symmetry, and the zeros or roots. Let's check these out using the parabola y equals x squared as an example.
The vertex is the highest or lowest point on the parabola. For y equals x squared, the lowest point is here, right? That's the point 0, 0. Remember, the vertex either has the highest or lowest point on the parabola. That depends on whether the parabola opens up or opens down. This parabola opens up. Here's a parabola that points down. This is its vertex, the highest point.
Okay, moving on from the vertex. The axis of symmetry. The axis of symmetry is the line that passes through the vertex and divides the parabola into two equal halves.
Here's the axis of symmetry for y equals x squared. Hey, for this quadratic equation, the axis of symmetry is the y-axis. It passes through the vertex here, and it divides the parabola into two equal halves, the axis of symmetry.
The zeros or roots of a parabola. The zeros or roots are where the parabola crosses the x-axis. All right, where the parabola crosses the x-axis. Since y equals 0 at all points on the x-axis, that means that the roots of a quadratic equation are the x values where y equals 0. Yeah, I know, that's a lot to digest. Coming up, though, we'll give you some good practice with all that stuff.
Parabolas! The vertex is the highest or lowest point on the parabola. The axis of symmetry is the line that passes through the vertex and divides the parabola into two equal halves. The roots of a parabola are where the parabola crosses the x-axis. Proceed.
There are a lot of different sports you can participate in these days. To be successful at many of them, it's essential to be in the right place at the right time. Take baseball, for instance. The path of the ball once it's hit is predictable. Whether it's a line drive or a pop fly, good players can generally anticipate where the ball is headed. But they have to react quickly and move instantly into position in time to make the catch. Let's look closer at a pop-up. If you collected and analyzed the data of height relative to time, what might you discover? Do you think that the height of the ball and the time it's in the air are related? How can you find out for sure? Platform diving is in many ways different from springboard diving. One difference is that platform diving is done at much greater heights. Platform divers also have to rely solely on their own strength to launch themselves into the air as they begin their dive. They need to be in the air a certain amount of time so they can complete all of their twists and flips before entering the water. If they don't get enough height off the platform, they can end up hitting the water before completing the dive and making a huge splash, which affects their score. How can you determine if a diver has enough time in the air to complete a dive? There are many different activities that show a relationship between height and time. How can you use quadratic equations to model these types of scenarios? How can you apply them to your favorite sports?
There are many different types of bridges. One common design uses a parabolic arch as a structural support. The Sydney Harbour Bridge has the local nickname of coat hanger because of its arch. Construction began on the bridge in July 1923 and was completed in January 1932. During that time, it took 2 years to build just the arch. The arch spans 1,650 feet across and reaches 440 feet above the sea. It took 42 tons of steel to construct it. The ends of the arch meet at a pair of pylons on both sides of the bridge. You can find steel arch bridges around the world. How can you use quadratic functions to model the shape of the arches of these bridges?
The wide use of smartphones and tablets has caused a boom in the app industry. Every day, developers devise new, innovative apps that track productivity, provide financial news and information, connect you to social media, or perform many other functions. Developing an app involves more than just a great idea. You have to design the interface, write the code that runs the app, publish it, and promote it so that millions of potential customers will want it. You also have to think about your revenue strategy. Some apps are free, but they make their money from in-app advertising. Other apps charge a one-time fee, such as 99 cents, when you first download it. Other apps are free, but require a monthly subscription to get the service the app provides. If you created the next big app, how would you go about setting its price?